In this video, we'll learn about the energy transfer equations for simple harmonic motion. Previously, we learned about energy changes or energy transfers in simple harmonic motion. The key concept for these energy changes is that as an object oscillates with simple harmonic motion, its energy is continuously transferred between kinetic energy and potential energy. If no outside forces do work on the system, the total energy of the object remains constant, so at any given point during the oscillations, the total energy is equal to the sum of the kinetic energy and the potential energy. In this video, we'll see how to derive formulae for the total energy, the kinetic energy, and the potential energy of an object that is oscillating with simple harmonic motion. To do this, we'll use three formulae that we learned earlier: the kinetic energy formula and the displacement and velocity formulae for an object oscillating with simple harmonic motion. Let's see what we get for the kinetic energy. Kinetic energy is equal to 1/2 mv squared, so we write 1/2 times m, and here we'll replace v with the simple harmonic motion velocity formula, so squaring gives us omega squared x0 squared times cosine squared omega t plus phi. Next we'll use the Pythagorean identity that you're probably familiar with from math, and which states that sine squared theta plus cosine squared theta is equal to 1. This means that we can rewrite cosine squared omega t plus phi as 1 minus sine squared omega t plus phi, which gives us that Ek is equal to 1/2 m omega squared x0 squared times 1 minus sine squared omega t plus phi. In our next step, we'll use the simple harmonic motion displacement formula. Rearranging this formula, we get that sine omega t plus phi is equal to x over x0, so here we can replace sine squared omega t plus phi by x squared over x0 squared. If we now expand the parentheses, for the first term we have 1/2 m times omega squared x0 squared times 1, so simply 1/2 m omega squared x0 squared minus 1/2 m omega squared x0 squared multiplied by x squared over x0 squared, so here cancelling x0 squared gives us minus 1/2 m omega squared x squared. So this is our expression for kinetic energy in simple harmonic motion, where m is mass, omega is angular frequency, x0 is amplitude, and x is displacement. Logically, kinetic energy will be a maximum when the second term in this expression is 0, which happens when x, so the displacement is 0. This result also makes sense because when x, so displacement is 0, the object is passing through its equilibrium position, where velocity is a maximum, making the kinetic energy a maximum as well. So we can write that the maximum value of the kinetic energy is equal to 1/2 m omega squared x0 squared. Now when kinetic energy is at a maximum, potential energy is equal to 0, so this expression also gives us the total energy of the oscillating object. Finally, as total energy is equal to kinetic energy plus potential energy, kinetic energy must be equal to total energy minus potential energy, and from this we can conclude that potential energy is equal to 1/2 m omega squared x squared. To finish up, let's see how we get the other simple harmonic motion velocity formula that is given in the data booklet. To do this, we'll start by rearranging the kinetic energy equation, which gives us that v squared is equal to 2ek over m. Multiplying the kinetic energy formula that we got below by 2 and dividing it by m, we can cancel the 1/2 and the m, which gives us that v squared is equal to omega squared x0 squared minus omega squared x squared. Finally, taking the square root and factorizing, we end up with v equals to plus minus omega times the square root of x0 squared minus x squared. The plus minus sign here is important because it indicates that the particle can be moving in one of two opposite directions. Keep in mind that on some exam-style questions, it is much easier to work with the second velocity formula. To complete our video, let's summarize the formula that we learned here, and let's add the variables. Note that the kinetic energy formula is not directly given in the data booklet, however, it is simply the difference between the total energy and the potential energy. With this, we have completed our learning about energy transfer equations for simple harmonic motion.